Okay. Okay, so are you there? Okay, the next person, Aditya Tunuguntla, if I'm pronouncing it correctly.
Yeah, yes, you're pronouncing it correctly only. Can you hear me?
Yeah, you're audible. You can just go
Is
ahead.
yeah, so my name is Aditya Tunuguntla. I recently completed my intermediate second year and I'm now going to join in BTech first year.
Okay, that's
Yeah,
great. And you're studying electronics engineering?
yeah, electronics and communication engineering.
And also to mention your colleagues. And
Yeah, so I recently took in my admission in WIT AP.
okay, nice. Thank you.
Thank you.
Next person, Ajo Raju.
Good evening, sir.
Good
My
evening.
name is Ajay Raju, and I am pursuing MSc Physics, first year student, Cochin University of Science and Technology.
Great. Okay, thank you. Next one, please. You can just see your names in the list as per the alphabetical order. Ankita Judile, if I pronounced correctly. Sorry for my pronunciation if I'm not pronouncing anyone's name correctly. Are you there? Okay, next one, Biswarup Datta.
Hi,
Hello.
myself Vishnu Datta. So I completed my MTech in Polymer Science and Technology from IIT Delhi,
Okay.
and currently I am working in the R&D department of Plus Advanced Technologies as a senior engineer, and I have almost now 2 years of corporate experience as working in the R&D.
Okay, great. What's your motive to select this course?
Okay, so the main objective was to learn regarding the fundamentals and to get along a little bit introductory knowledge about the semiconductors. So my basic and basic motive was to learn regarding the fundamentals.
Okay, cool. Perfect. Thank you. Next person, Brunda D. Kale.
Good evening, sir. My name is Brunda D. Kale. I'm recently completed my first year. I'm studying in Global Academy of Technology.
Thank you. Next one, Chandana D. Hello, are you there? If not, then we can move on. Next person, Charvi Kinjarapu.
Good evening, sir. Myself Charvik Indirapu, and recently I've completed my second year in Rishi MS of Institute of Engineering and Technology for Women.
Okay.
Thank you.
Okay, thank you. Next person, Dhirangulla Shrikant.
Hello, good evening, everyone. Currently, I am pursuing in the BTech in Electronics Communication and Engineering. So, I recently completed my diploma in electronics.
Okay,
I started learning about the semiconductors in this course.
thank you. Next person, uh, Inchara.
Good evening, sir. Myself, Inchara. I am pursuing BTech Engineering second year at Global Academy of Technology from ECE branch.
Okay, thank you. Next person, J. Santosh Valmiki.
Good evening, sir. Myself Vijay Santosh. Recently, I have completed my first year in Vignan Institute of Information Technology, Vizag. Thank you, sir.
Thank you. And next person, Manusri Selvaraj.
Good evening, sir, and good evening to everyone. Sir, I recently completed my second year in ECE department and now I am a third year student, sir.
In electronics.
Yes, sir.
Okay, thank you. Please mention your branch
Thank
as well, everyone. Next person, Muthu Soumya. Are you there? Okay, it's fine if you don't want to introduce yourself. The next person, Nagaram Pallavi, with some roll number over there.
Good evening, sir. My name is Nagaram Pallavi. I'm currently pursuing my third year engineering in CMR Institute of Technology, Hyderabad, and I'm in electronics and communication engineering pursuing.
Okay, great, perfect. Thank you. Next person, mm, Narasimhan Narasima.
Good evening, sir.
Good evening.
My, my name is Nasim, sir. I'm 2024 passed out ME VLS design, sir. Then I'm recently working and yes, Sri Venkateswara Engineering and Technology.
And what do you want to opt for this course?
Sir,
Why do you want to opt for this course? Or what's your motive to study this course right now?
fundamentals, basic information, sir.
Okay, okay, it's fine. I got it. Thank you.
Okay.
The next
Hmm,
person with some roll number over there and Sanchit.
Good evening, sir.
Good evening.
My name is Sanchita. I have recently completed my second year electrical and electronics engineering at NMIT NITTE.
Thank you.
Thank you, sir.
The next person, Ojasvi K.
Good evening, sir. My name is Ojasvi. I'm currently pursuing second year of my BTech in ECE. My college is Bhoj Reddy Engineering College for Women.
Thank you. Next person, Pavani Virupakshan. I guess it's Pavani, yeah.
Good evening, sir. This is Pavani Virupakshan from Global Academy of Technology. I'm currently pursuing from my second year BE degree in the same college.
Thank you. Where is this Global Academy of Technology exactly?
It's actually in the RR Nagar side of Bangalore.
Oh, it's in Bangalore. Okay, fine.
Yeah.
I could see there are a lot of people from this college. Thank you.
Yeah.
Prasant G. Prashant G, if you want to introduce yourself. Otherwise, you can go to next. Ratna Sagar Patra.
Good evening, sir. My name is Ratna Sagar Patra. I am from Bhubaneswar, Odisha. Currently, I am pursuing BTech in BTech final year in CBT1 Global University, and my domain is ECE.
Okay, great. Thank you. Sanjeev Garje.
Thank you.
Next person.
Good evening, sir.
Good evening.
Sir, I have been
You have some background noise coming in. I cannot hear you properly.
sir, I have been working at police department
Okay.
as well as have been studying from India study center Pilgrim.
Okay, fine. Thank you. There's a lot of background noise coming from there. Thank you. Next person, Sarika Gopinath.
Yes, sir. Good evening.
Good evening.
I'm Sarika, currently pursuing second year of EC department from Sri Muthukumaran Institute of Technology, Chennai.
Okay, thank you. Next person. What is this? Is it Sasima or SAS? I don't know. Okay, let's move on to next. Sharanya Malla.
Good evening, sir. My name is Sharanya. I'm currently pursuing BTech second year in Rishi MS Institute of Technology in Hyderabad.
Okay, thank you. And next one, it's me, and then it's Srinithi J.
Good evening, sir. I am Srinidhi, currently pursuing my second year of BE ECE at Ramco Institute of Technology. Thank you, sir.
Thank you. Yeah, Sasima, you can go ahead. You can just introduce yourself.
Yeah, good evening everyone, and this is Sasi. I'm working as a project manager in Bosch Limited, and the motive behind this course is I want to become a project manager for semiconductor industry. So I just want to brush up myself with the basic knowledge on semiconductors.
Okay, thank you.
Yeah.
And next person, Shivali Yerubandi. Yeah, Srivali. If you're there, no. Let's move to next. Subhashini V. I could see there are 31 people now. Subhashini V, if you're there, you can introduce yourself quickly. You're not audible. You have turned on the microphone, but you're not audible. Not yet. I mean, okay, it's fine. You're not speaking right. Hello. Okay, let's move on to next. Yagumneha Yadav.
Hello, sir. Myself Neha. I'm pursuing my BTech in ECE. I want to gain some knowledge in semiconductors.
Okay, fine. You are in which college exactly?
I'm from Vignan Institute of Information Technology, Vizag.
Okay, thank you. Okay, so we're done with the introduction. So there are a lot of people from other many institutes, mostly I could see from middle and southern part of India, if I'm correct, mostly from Chennai, Hyderabad, Bangalore, and yeah, I mean that's what I understood from your introduction. And if anybody else joined in the meanwhile, then maybe you can introduce yourself quickly in case in next 1 minute. Then we're going to start with the week first module, what we're going to cover in this. And in any case, anyone else who joined? Okay. I don't think anyone else joined then. Okay, so about myself, let me introduce myself also to you guys. Maybe right now there are 30 people, but maybe the number can reduce with as we go on into this module, or it can increase. Mostly the pattern is that it reduces with every module because of other secondary effects. So I'm Shazan, and I am a PG student at IIT Bombay and also a DAD fellow at Technical University of Berlin and a research institute, a Paul Brood Institute for Solid State Electronics. And I'm doing PhD there in the field of solid state electronics. That is basically semiconductor devices. About yeah, we are working in semiconductors, not exactly the devices, but on the, I should say, applied physics part of it. So my field of research is something called as phononics. And phononics deals with the study of phonons and electrons and their interactions. So this is the brief introduction about me. So if you guys are interested in doing research in it, you can contact me anytime, or you can just get in touch with me. And yeah, if you guys have any doubts, you can just text me over the email, or you can just get in touch with me. Okay, so let me just okay. So we are into week first of this course. I don't know why this is heating up so much. So we are into week first of this course, and as you might have seen from the video lectures of Professor Naresh K. Imani, you might have studied, or I should say, correct me if I'm wrong, but you might have studied about the basics introduction to semiconductors. You might have covered in the video lectures about the classical versus quantum mechanical effects in semiconductors or semiconductor crystals. And then you might have seen about maybe certain effects which come because of doping. What are the concepts related to doping of semiconductors and how you can deal with these doped semiconductors, which are different from the undoped semiconductors or intrinsic semiconductors. Then I believe you have also studied about certain maybe uh, when you study quantum mechanics, you have studied a little bit about quantization of these energy levels. Energy levels. Okay, so this is the first week one that you might have seen in the video lectures. And let me just try to briefly tell you that what this session is all about. In this session, we're gonna solve some problems, but it's not gonna be a general problem solving session. It's also going to be some, I should say, the basic concepts. No, this should not be like this. Basic concepts of semiconductor devices are also gonna be revised. So with each question we're going to solve, we're going to go deeply into the concept of that question, and we're going to discuss what things are necessary in order to understand or solve a particular question. So it's not going to be, let's say, for example, we have first question. This first question, if you have a very good knowledge of semiconductor devices, or if you have watched his lecture carefully, if you have watched lecture of Professor Naresh Imani carefully, you're going to solve this in maybe 20 seconds or 30 seconds. But that's not the goal of this session. The goal is to at least go in depth of the concept of this particular problem, and then finally we're going to arrive at some particular answer. The answer to these problems is going to be simple, but we're going to arrive to that answer in a deeper way, to develop the deeper understanding of the concept behind it. So that's going to be the goal for this. And most of the time this session will go on for maybe 1.5 hours, and hardly it will go up to 2 hours, depending upon what sort of concepts we are dealing with. If we go into week 5 or week 6, maybe we're going to go to 2 hours, but mostly it's going to be limited to 1.5 hours. Yeah, and all of these lectures are going to be recorded, so you're going to find the recorded lectures on YouTube. I guess you guys have the link in the Google sheet. Link is in the Google sheet, and you can find the recorded lectures on the YouTube, and you can also find the previously recorded lectures of the same course. So it's the same course, Introduction to Semiconductor Fundamentals 2025, offered by NPTEL, and it was under the same instructor, Professor Naresh Imani. And you can find it on YouTube as well, where I have basically gone in detail about certain concepts. Let's say in week 2 and week 3 there, I have discussed in detail about the chronic penny model and chronic penny model, which is basically to understand the band structure of the semiconductors. So in case I just don't want to throw the jargons right here, but in case if you guys are interested in deeply analyzing the concepts, there I have spent a lot of time. Even those videos are maybe 2 hours, or some are 3 hours. A lot of time in order to uh, basically make you understand these particular concepts in a simpler way. And I've done it, I guess, last year in autumn or something. If you guys can just, you guys can go to this YouTube link and you can find these courses over there. Okay, so what is the first thing that you might have studied is, let's say, okay, yeah. So we're gonna quickly brush up, and we're gonna reach to a level wherein we understand what is basically happening inside a semiconductor and how we understand that. So for that, we're gonna need certain basic concepts from maybe electrostatics, which comes from 11, or which comes from 10 plus 1 and 10 plus 2 classes. So you guys deal with some basic electrostatics. You guys deal with how basically charges. You can please mute yourself. Whoever is speaking, Vishnu Priya S, can you please mute yourself? Thank you. Otherwise, I can also mute you from here. It's fine. Okay, so you guys have studied in your 10 plus 1 or 10 plus 2 about electrostatics, but if you don't have, just don't worry. I'm not gonna I'm not gonna everything is not gonna boil down to those particular concepts, although it boils down to those concepts, but I'm gonna try to simplify these concepts as simple as possible. And the first thing to note about before we study any semiconductor, what we study is basically atoms in a crystal. So how do atoms in a crystal behave? So if you have a crystal, or if you have a crystalline structure, a material, let's say this is a material, some material. We don't know, let's call it material A. And if you have regular arrangement of atoms, inside the material there are atoms present inside it, which are the microscopic entities, cannot be seen with the naked eyes or with the advanced instruments even. So these atoms, that they have some electron cloud present, which you have studied this from the basic fundamental courses. Now, what you have studied is that because of this, if you take single atom, let's take single atom because it has a huge nucleus in the center, so it has a huge positive charge in the center, and around it there's a negative electron cloud. So similarly, it goes for all of the atoms. Okay, you have a positive charge, you have a electron cloud surrounding it. Okay, let's take only a single linear line of an atom. Okay, we're going to deal with the other dimensions later on. I took this linear chain of an atom. So what is going to happen is that that these electrons, when they are in the vicinity of this atom, they're going to face electrostatic forces, because electrons are negatively charged and this is a positive charge, so there's going to be the Coulombic repulsion and attraction forces. So there's going to be forces which are basically electrostatic forces, and because of which you have the potential energy profile of an electron. So electron is going to feel the potential energy, which is basically U, because of this positive charge. Okay, it's as if you have a positive charge and you have some negative charge, what you call in basic electrostatics as test charge, and you bring this negative charge close to the positive charge, and you see how its potential basically behaves, potential energy. And once you see that potential energy curve, can you please mute yourself? I'm getting disturbed because of it. Samuel P. Okay, I'll just mute you. Please ensure that you don't unmute yourself unless you don't have any questions. So because of this potential energy profile of an electron around the nucleus, when you draw those potential energy profiles, you have a nucleus here, you have a nucleus here, nucleus, nucleus. So it's going to look something like this. This is the potential energy profile of an electron. This is the potential energy. So this axis is U, this axis is R. R means it's spatial space axis. It can be X, Y, Z. It depends upon, if we are talking about this dimension, it's X right now. So this R is right now X. So R can be X, Y, or Z. Okay, right now we're talking about X. So this is U as a function of R. That means this is the potential energy profile as a function of distance R. And you know that this is inverse relation to R. This is like a hyperbolic relation. And so the potential energy profile varies like this. So this is for the electrons in this particular electron cloud, and for the other electron, which is for the other atom, is going to face again a similar potential energy, and for another atom it's going to have the same potential energy profile. For another atom is going to have similar potential energy profile. Now you draw these weird shapes, but this is nothing but a potential energy profile of an electron felt in presence of atoms, which are basically the nucleuses. Now what happens if you carefully look at these curves now, because these curves now intersect here, you can just remove these parts, you can just remove these parts, you can just remove these, and this is the exact potential energy profile curve you see in the books. So you have a potential energy profile like this, and then you have a potential energy profile of an electron just like this. And what does this indicate here? This over let me just remove it. This end and this end, this represents basically the ends of the crystal. Okay, these are the ends of the crystal. So you see that this potential energy profile is huge towards the ends of the crystal. And similarly, it's over here. Okay, and now what happens? Now, how do you solve this particular problem now? Now, because you need to understand this mathematically, so what you do is that you take one of these weird shapes. Let's say, for example, maybe you take this one. When you take this one, you have a shape like this, which is a hyperbolic profile. This is a nucleus, and that means we now have to show where exactly is the electron in presence of this electrostatic potential. So what you do for that, you simplify this problem and you don't consider the curvature of these hyperbolic curves. What you do is that you consider it to be a rectangular shape. Okay, so this is basically approximated by rectangle, something like this. Okay, and this is basically now your potential profile. So this is the potential profile of an electron in presence of a positive charge. This is not the exact, but this is the approximation we make. This is the exact. But in order to solve this, it is a little bit tricky mathematically. We can do it, but in order to do it by hand, we always approximate it with rectangular potential. Okay, once we do it, now the problem simplifies. Why? Because now you consider, let's say you assume the electron to be somewhere, and now you consider the electron's wave function, some psi as a function of x. I told you it can be psi as a function of r, but here r is basically x, so it's psi as a function of x. This is x dimension. I wrote here r, but this is actually x, just like I told before. So this is now representing the something called wave function of an electron, but we don't yet know what it is. How do we arrive at that particular problem? We're not going to solve mathematics here. We're going to understand the concept behind it, that how you arrive at the exact band diagram and the band structure of an electron. And once you have this rectangular profile, once you have this rectangular profile, potential profile basically, so it's a u as a function of x. Now what you do now, you solve the Schrodinger equation. You solve the Schrodinger equation for an electron. Now when you go into Schrodinger equation, it's a quantum mechanical equation. But what is quantum about the Schrodinger equation? Because it represents electron not as a particle but as a wave function, which is psi of x. Okay. And which Schrodinger equation do you solve? You guys have seen the Schrodinger equation as minus h bar square over 2m dou square psi over dou x square. Oh god. Just give me a moment. What happened? Sorry for this interruption. So you have seen the Schrodinger equation, which is looks minus h bar square over 2m. What is happening? Minus h bar square over twice m dou square x over dou square psi over dou x square plus v of psi equals to e of psi. Now what is the Schrodinger equation exactly? You guys know, if you just separate this Schrodinger equation, you're gonna get something like h psi equals to e psi, where this h is basically Hamiltonian. I'm not gonna throw jargons at it, just forget about the terms, but this basically represents the total energy. If you are dealing with total energy, it is basically minus h bar square over twice m dou square over dou x square plus v. This is basically called as Hamiltonian h. So it encompasses the kinetic energy part as well as the potential energy part. This is the potential energy part of an electron. This is the kinetic energy part of an electron. Okay. And what you do is that you essentially solve this particular equation. Now, what is good about this equation? It's a differential equation. Okay. It's a partial differential equation, and here you have the simplistic thing about this is you have a psi as a function of x only, because we are dealing with one dimensions only. We are dealing with psi as a function of x. And now you do certain tricks. You just solve this particular problem. You write it as dou square psi over dou x square minus 2m over h bar square V minus E of this will be plus, this will be psi, this will be psi equals to 0. So you just bring it on the other side and you simplify it. We're not going to solve it, just don't worry. We're going to just arrive at some basic equation. You're going to get minus twice m v minus e divided by h bar squares psi equals to 0. And this is going to look something like, maybe let's call it k square psi equals to 0. You can call it any k square or k. So this is the exact differential equation which we solve. And how we arrive at it, how we arrive at this differential equation, it's simple. You take a Schrodinger equation, you just write Schrodinger equation for this potential where this v is some potential. I wrote it u, pardon me, let's write it v. We can write u, we can write anything. So this is v, which is the potential energy of the electron inside this particular rectangular profile. And you arrive at this particular equation, you simplify it, you arrive at this particular simplistic differential equation, which is dou square psi divided by dou x square minus k square psi equals to 0. And this is exactly, not square root, twice mv minus e over h bar square. So you can write k as square root of twice mv minus e over h bar square. And now you guys know from the basic mathematics how to solve the differential equation. You assume a solution. You just assume that psi is either exponential, it's either sinusoidal. So this psi, if you can assume, it can be exponential, it can be sinusoidal, it can be cosinusoidal. These are just the basic tricks you can play to solve the differential equation. You just assume psi to be something, then you solve for that particular psi. We're not going to solve this differential equation. What we're going to show is that how we arrive at that at particular energy profile of the I should say electron. Now, once you solve it, what's the solution that you get from this psi? The solution that you get, it's basically psi as a function of x, which is basically, which it gives you information about the uh, wave function of the electron. What it also gives you information is that in order to solve this particular differential equation, you need certain conditions. What are those conditions? You need boundary conditions. Boundary conditions. And what are the boundary conditions in this case? That means you should be exactly knowing what is happening to the wave function at some x equals to maybe 0 and some x equals to other dimension. That means if you take this rectangular well, you now have to make it sort of a mathematical, in order to make it mathematically rigorous, what you're going to do, you're gonna assume some dimensions of it. Let's call it, let's say the width of this well is this particular thing. Let's call it, let's say it's L, and let's call this particular point as 0, this as A, and let's call this as B. Okay, so let's remove this. So let's call the width of the well as A, and let's say this particular dimension is A plus B. It's just like a square modulated wave, wherein you have the width of this as A, and the period, which is, period means the repetition of this well. This is the period. So this is basically being repeated over and over again in this particular lattice chain. So this is A plus B. Okay. Now, what you do is that you use a very important condition, which is basically called as Bloch's theorem. You might have again heard about these things. I'm just trying to recap all of those things without going into the details. You use Bloch's theorem. And Bloch's theorem in basic sense says that if you have these rectangular wells, and if you have electrons over there, because there is electron cloud in every of those wells, then if you know what is happening to an electron in this particular region, you can essentially guess what is happening to electron at some other, in some other well. Let's say this is point x dash. That is the essence of the Bloch's theorem. And essentially how it does is basically, it comes from mathematics. It just comes from pure mathematics. It comes from Fourier series analysis, but I don't want to go into the Fourier series analysis right now. Okay, it comes from Fourier series analysis. If you guys are interested, you can just go and look at the Fourier series of a square wave and then see what are the factors, basically how you can arrive at the Bloch's theorem using the Fourier series. But that's not what I want to make you understand, because if I start writing mathematical equations, it's going to take a lot of time. So the essential understanding is that if you know the wave function of electron in this particular region, you can get the wave function of electron in other region, but there is a phase factor associated with it. I mean, if you can get the wave function at this particular point, except that there will be some phase term associated with the electron. This particular phase term. What is this phase term? Phase term is that if you have an electron moving like this as a wave, let's say this is electron wave, this is electron wave, a simple sine wave. Then if you, in case your electron encounters any of this scattering or anything happens to the electron wave, it's going to look something like this. Okay, so here you see that the phase breaks basically. So this is called phase breaking events. And once you consider electrons in multiple of these quantum wells, you have to essentially consider the phase term which is associated with basically these electrons. So your electron in these quantum wells are going to be, they're gonna look similar, except that there will be some phase associated, which is basically spatial phase, space associated phase, because there is x term. Okay, so your wave function at x plus some x dash is gonna be some wave function at x into e to the power ikx term. Now what is this k? Now this is a different story altogether. Where does this k come from? Because it's associated with the wave vector of an electron. What is a wave vector of an electron? Now this is the important question. So in simplistic terms, this is associated with the wavelength of an electron. Just understand in that context, because this is inversely, the wave vector is inversely proportional to the wavelength of an electron. Okay, so in essence, your phase factor is associated with the wavelength of the electron. Okay, and now what do you do? What you do after this, you do a lot of things. You use the boundary conditions, Bloch's theorem, what you call as Bloch's theorem. You put it into this particular equation and you solve this particular equation. Once you solve this equation, what do you get? You get the solution of this particular differential equation. You get the solution of this particular differential equation, and that solution essentially gives you something called as band structure of an electron. I am skipping a lot of points here, but I'm just trying to make you understand where does the band structure of electron come from. That means, what is the band structure of electron? Essentially, you would have thought that the solution of this will give you psi, but it gives you the psi, no doubt, but it also gives you energies. It also gives you energy. That means this energy, this particular energy, it gives you energy as a function of k, which is basically the wave vector of an electron. So you can essentially get curves mathematically about how the electron energy varies with different electrons wave vectors, and what are those wave vectors, and why are we concerned about this? So this band structure, which you call as E versus K, it comes from this. It comes from the solution of this particular thing, and this entire thing you might have studied under the name of Kronig-Penney model. This is just a name, and it's not necessary to remember the name, but it's necessary to understand the concept. You can just forget the name. The concept is this, that you obtain the particular band structure once you solve these equations, what you call as, in general sense, Kronig-Penney model. And once you solve this, now what do you get? You get this E versus K plots, which is basically uh, energy versus what you call as wave vector. You can also call it momentum. How can you call it momentum? I just called it wave vector. You can just call it also momentum of an electron, because momentum of an electron is h bar times k. So if you write the p, which is momentum of an electron, it's h bar times k. So when you're plotting energy versus k, it's as if you're also plotting energy versus momentum of an electron. Okay, in different directions of the crystal. Now the different directions are essentially important. Now once you get it, you get something like this, which is basically uh, energy versus k diagram. Now what are these exactly? And once you get a solution, for example, you get a solution which looks, you get a solution of that equation, it looks something like this. It looks something like this. Now let me try it like this. Then you get something like this. You get these curves if you have seen in the books. Okay, and the essential thing about these curves are basically they represent the energy states of an electron, the acceptable energy states of an electron in a crystal with different k directions, with different wave vectors. What does it mean now? It means that once you have a crystal, essentially what you have, let's say for example, you have a maybe you have a crystal which is, let's say, hexagonal in shape. For example, you have a crystal shape which is hexagonal crystal structure. 1, 2, 3, 4, 5, 6, and these shapes repeat over and over again. Let's say for example, this looks something like this. God, no, 3, 4, 5, 6. Okay, so this is gonna repeat in different directions. This is one of the example. Oh, not all the crystals are hexagonal, and not all the other crystals can be cubic. They can be something like this, simple cubic crystals. Just like, for example, you might have heard about sodium chloride crystal. It's cubic. Something like other forms of the crystal, for example, silicon. It has some other shape. For example, if you have gallium nitride is a semiconductor you might have heard about these days. It's hexagonal in structure. Okay, it's exactly the shape is something like this. It's something like this. This is the shape of the gallium nitride. But I don't want to go into the details of it. I just want you to understand that what does this exactly represent then. So once you have a certain crystal now, because there are atoms located at these particular sites. So if for example you are looking at gallium nitride, that means you are looking at the top view of it. So for example, this is hexagonal. This is the gallium nitride crystal. That means you're looking from this side. You're looking at the top of this crystal, and you're essentially looking at these particular hexagons. Now, for example, you choose a point in the center of this particular hexagon, and you go into different directions. You go in this direction, you go in this direction, you go in the other direction, you go in this direction, you go in the other direction. So these are the directions basically associated with the crystals. And for example, if you have a center point, or what you call as a I should say the high symmetry point, what you call as gamma point also. If you go into other direction of it, you go into some other point, you call that X. I'm just naming them, not as per their sequence. You go in some other direction, you call that M. You go into some other direction, you may call it R. You may call this Z. You may call it maybe M dash or something. So these are different direction indices. Direction indices. Again, you might have heard about something called as Miller index or something like that. I don't want to go into that again. Just understand that these are directional vectors uh, of how the electron's energy essentially varies inside the crystal. That's it. And that is basically what you get from this curve. So you get this curve as a solution of that particular equation. But how do you understand this now? What you do is that you might have done that you backfold these particular curves. You backfold them into the first curve itself, something called as This particular representation is called as extended zone representation. Extended zone representation means that you have these energy curves throughout the K space. But in order to fully understand them, because we are mostly dealing with this particular part of the EK diagram, reduced something called as reduced Brillouin zone, you want to essentially fold all of those energy curves into the first Brillouin zone itself. You don't want to deal with the other higher, I should say, extended zone representation. You want to simplify this curve as simple as you can make it. So what you do, you backfold these curves into the first Brillouin zone, and that is what you essentially see in your books, that your EK curve now looks something like the first curve remains the same, because it's not, oh god, what is happening to this? Hmm. So let me just remove it. So this curve remains same, there is no backfolding, but this gets backfolded and it looks essentially like this and this. So this comes here and this comes here, it backfolds. So all of those curves are essentially now backfolded and they look something like this, something like this. The x's remain same. This is E versus K axis. So now you see what has happened is all of those curves now you traced into the first zone itself, first zone only. Now you can understand that these curves essentially represent the energy of an electron. And how do you now understand the energy of an electron? For example, these are these are the innermost curves. These are the innermost energy levels of an electron, and these are the outermost energy levels. That means from your basic fundamental understanding of even physics or chemistry, you know these innermost energy levels, what do they represent? These are like just like inner orbitals, okay, like s orbital and some inner completely filled orbitals, okay. That means these energy bands are essentially completely filled. Now, why am I saying completely filled? Because you're not only dealing with single electron, you're dealing with multiple electrons, lot of electrons. Okay, so essentially your lowermost energy bands, these are basically inner energy levels of an electron, just like you have inner s orbitals of a single atom. Just like, for example, you have a positive charge and you have a nucleus, just like these energy levels. So innermost electrons, let's say these are two electrons in the s orbital, and then you go on up and above, you have more electrons in it. This is the case of a single atom. But here, why do we have so many electrons? And why does it form an energy like a band now? Because now there is not single electron, there are multiple electrons. Multiple electrons going to form this particular energy band like structure. And now those electrons are going to occupy spaces in this particular energy band. So these energy bands represent the innermost energy levels of an electron. And similarly, let's say, for example, this is also filled. And these outermost energy levels are something like if you consider the single atom, these are like the p orbitals or external outer or valence orbitals of an electron, of an atom. But this is right now we are considering a lot of atoms together and forming an energy band. Now, this is the case of a semiconductor. What happens in a semiconductor? Because now you moved from a single electron picture now to a multiple electron picture. And now you're considering that those electrons are not in a single orbitals, but they are forming a band of energies with in different wave vectors inside the crystal. Now what happens? Now this is basically the energy levels of a crystal. And essentially what you call as I should say valence band, is basically the top of this particular band, and what you call as conduction band is basically the bottom of this particular band. This is how you essentially arrive at the picture of valence band and conduction band. That means now you take out these particular two bands from it. That means, for example, if you can if I can just duplicate this. Come on, duplicated everything. That means now if you take the top of this particular band, which you call as valence band, and the bottom is called as conduction band. Now what? Now, because this valence band is like a completely filled band, I mean it has electrons throughout. Right now I'm only dealing with electrons. I'm not talking even about the holes right now. Let's forget about holes. Okay, let's talk only of electrons. We're gonna arrive at the holes eventually, but let's talk only of electrons. So this entire valence band is basically, I should say, completely filled with electrons. And these are like the innermost electrons. Now what happens? In this particular state, this, for example, if this is a crystal with this configuration where you have the completely filled valence band, but there is no electron in the uppermost band, then it's not gonna conduct anything. Because for conduction, you need electrons here in the conduction band. Only then they can be essentially modulated by the electric field. Only then, for example, if you have a crystal, if you have some crystal, let's call it crystal A, and if you apply electric field to this crystal, you apply the voltage or a battery or something that's going to apply electric field. What do you do? That means you make this end as positive, you make this end as negative. The electric field is going to be from positive to negative. Electron is going to feel the force in the opposite direction because force on electron is minus q times the electric field. There's a negative sign. So it's gonna feel the force in the opposite direction. But which electrons are these electrons? These are not valence electrons. No way. These are not the valence electrons that feel the force, because in this particular picture, you assume that the electrons which feel the force because of electric field, they're essentially free electrons. Or sometimes you can call them nearly free electrons, because an electron is never free. Okay, that is a sad truth, but electrons are never free. So in a crystal, when you apply the electric field, you expect the electrons to move in the other direction, and then you expect the current to flow. That is essentially what happens in a normal conductor. But which electrons are we talking about when we apply the electric field? The free electrons are going to move. The bounded electrons, which are in the innermost orbitals, here, these electrons, they are not going to move because they are bounded. They are in the innermost orbital levels. And we can also understand them in this particular picture. That what happens if you have bands like this. These are innermost bands. This is the innermost band. This is the outer band. Let's say this is the conduction band. This is the valence band, and then you have electrons present here. These are the electrons. This valence band is completely filled with electrons. Okay. If you apply electric field in this particular scenario, your electrons essentially are not undergoing any drift or motion in this particular picture. Why? Because there is, I should say, you can understand it just like this. You have just like a, what do you call that? A bead. You have a bead with some. You have a string, but with beads. These are like beads on a string. And if you want to, let's say, move this particular beads in one direction, you can essentially apply force here, and this bead is going to move to the other direction. But this is going to be a restricted movement of the electrons, and it's not going to be free movement of the electrons. What happens if you just remove one of the electrons? If you just take out this electron is then going to move. It's going to move freely here. It's going to move here, and then there will be vacant site here, the electron will come here. Then this electron is going to move here, there will be vacant site, this is going to move here, this is going to happen, and this is going to be essentially happening, and it's going to lead to some flow of these particular electrons. But because if your string is completely filled with beads, your flow is going to be restricted. That's what essentially happens in the valence band. Your electrons are completely occupying the energy levels. Now, what you want to do essentially, you want to make some electrons free. You want to create some space for them so that they can flow freely inside the crystal. That is where the concept of holes come from. And this concept of holes is very, very deep in terms of quantum mechanics, but I don't want to go into that detail. I just want to touch the basic fundamental levels. So what you do is that you essentially create a hole. How you create it, that's a different scenario, but let's talk that in a different session, how you do that. Maybe doping, maybe something else. But what you do, this is right now we are talking about this valence band. You remove one of this electron, and when you remove this electron, where is it going to go? You're going to throw it into some other band. Maybe you're going to throw it into some maybe conduction band, or maybe there are some other energy levels which come because of what happens because of doping. Is we're gonna talk later on, but let's say it's going to go into conduction band, and you're going to free some more electrons, and they're going to go into conduction band. You're going to have some free electrons in the conduction band, and you're going to have some holes here in the valence band, because now you have free space. There will be some holes, there will be some holes, there will be some holes. Now you apply electric field. What are you going to do when you apply the electric field? This is valence band, this is conduction band. So this is the electron, this is the electron, 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 hole, 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 hole. Now if you apply electric field in this direction, what is going to happen? Electrons are going to feel force in the opposite direction, this direction, and holes are going to feel the force in the same direction as that of electric field, because holes are positively, I shouldn't say they are positively charged, but we treat them to be like a positive charge, but they are not positive charges. Holes are just vacant orbitals. They are just vacant orbitals from which the electron has left, and you have something called as hole. It's just as a layman sense we call that hole, not in a quantum mechanical sense. That's a different story. So essentially what you now have, because if your electrons are moving in this direction, this is electron motion, the holes are moving in this direction. So when your electrons move in this direction, your holes move in this direction. So your current flows in the opposite direction as that of electrons. That means your electronic overall current, not the electronic current, your overall current is going to be in this direction. So your overall current is going to flow like this, something like this. But we are showing it on a band structure. It's tricky. Don't just mix it with the other crystalline structures. So this is the motion of an electron in a band structure. Okay, how does the motion of electron happen in under the influence of an electric field? Now, how do you create these particular holes and vacant spaces? You do sometimes you call something called as doping. You intentionally introduce some atoms. Just like, for example, you have a silicon. You have silicon atom which is bonded to four other silicon atoms, just like this. Silicon, silicon, silicon. You might have heard about this in your primary introduction courses in electronics also. So silicon, that means it has four electrons. It has one, two, three, four. No, not here. It has four valence electrons. Okay, it has four valence electrons on each atom. Now, what happens if you just remove one of the silicon and you put maybe a phosphorus here? Phosphorus is a pentavalent atom, that means it's a group 5 element, and that means it's having 5 electrons now. It's not going to have 4 electrons. Where is this one electron going to go? This is exactly the one electron which takes part in conduction. Because of this one electron stays basically in conduction band. Okay, and when it moves, it's going to play a role in conduction. And that is why when you dope, for example, a silicon system with phosphorus impurity or maybe antimony, arsenic, something like this, it's gonna form something called as N-type semiconductor, because the dominant carriers of the current are gonna be electrons, and for like electrons here, because there are more free electrons compared to that of the holes. So not in terms of the current, there are more free electrons compared to that of the holes. That's why N. But instead, if you just dope it with that, if you take it out and if you dope it with let's say boron. Boron is having only 3 electrons in its valence shell. The other shell is going to be empty, and this is going to act like a hole. And what is going to happen? The electrons from nearby sites can hop and they can go into this hole. They're going to fill this hole. That means, for example, let's say there's an electron and it hops to this particular place. It fills this hole. Once it fills this hole, the hole is going to come up here. So it's as if the hole has moved in the crystal, but it's not actually the hole that's moving, it's the electron that is moving. Okay, just understand this picture. So essentially the electron moved from here to here, but it appeared that as if the hole moved from here to here. So that's why the hole motion is opposite to that of the electron motion, because of this particular, I should say, motion of these particular electrons. But it essentially is creating a vacant orbital. So once it does so, it results in conduction of these particular conduction process. And for example, if when you dope it with like a trivalent impurity like boron, you form something called as p-type semiconductor, because now you have more holes compared to that of the electrons. Essentially, you call it as p-type semiconductors. But it's very tricky if you look deeper into the materials itself, and if you understand the concept of holes and electrons, you will in the end say that these are all happening because of the electrons. There's no hole. But just don't get confused because of it, because there's a deeper picture behind it. So it's just I should say layman understanding of, to understand at least the free electron motion inside the crystal. So now you have these free electrons in the conduction band and valence band. This is the conduction, this is the innermost band, this is the valence band, this is the conduction band, this is the valence band, this is the conduction band. So now you have some electrons here, you have some holes over here. They're gonna move and they're gonna I should say take part in the conduction. Now, the tricky part. The tricky part is, now you have to pay attention, because this, whatever I draw was E versus K. It was electron's energy versus the momentum of an electron, or the wave vector of an electron inside the crystal. And how do you understand it in terms of real space? Real space is the space we live in. Let's say I give you a piece of silicon. This is a piece of silicon, and I tell you to apply some current on it, apply some electric field. Your electrons are gonna, let's say, flow in this direction, and your current is gonna flow in this direction. So your current will flow in this direction. How is it connected to this case space representation? Because this is real space. This is the space we live in. You understand? If I give you a piece of silicon like this, if I give you a piece of silicon, which is let's say it's not exactly square. Piece of silicon is, if I give a wafer, silicon wafer, which is circular. So this circular wafer has certain thickness. It has certain thickness. Okay. And essentially, what you do is that if you take, this is the top of the silicon wafer, and this is the bottom of the silicon wafer. If you deposit some metal over this, it's like a contact. It's like a contact, just like you make some metallic contacts to apply the electric fields, just like electrodes. These are like electrodes. If you apply 2 electrodes over the silicon, and if you connect this to positive end, you connect this to negative end, and the electron is going to flow in this direction, the current is going to flow in this direction. So there'll be current flow in this silicon, essentially. And but this current is basically flowing in real space. Okay, if you consider this circle, then even if you, let's say for example, let's for now consider this to be x direction, this to be y direction. We are considering it to be circular, not a sphere. Then you need to consider the spherical coordinates. Let's consider the Cartesian coordinates right now, x, y, z. Let's ignore z. Let's ignore the thickness. So your current is basically moving in this direction, or your electrons is moving in this direction, in minus x direction, and your current is moving in from this positive electrode to the negative electrode. What is happening, and how can you relate this k with this particular x? That is the trickiest part, which most of the people don't understand. What is this? What is the relation between this k and x? Essentially, you know what we call this band structure. There's another thing that you call as band diagram. These are two different things. Don't get confused by band structure and band diagram. They are two different things. Band structure is E versus K. Band diagram is E versus X, real space. It can be E versus X, E versus Y, E versus Z, but in real space, not in a key space presentation. And again, I'm not going to go into mathematics of it. Okay, because if you want to understand it, you need to understand it mathematically. That is the only way to understand it, because it's a very, I should say, uh, imaginary type of concept to go from K space. What is a K space and what is a real space? We all know, but what is a K space? Inverse space, something like the space in which you essentially make the band diagram. That is why I initially mentioned that if you have little bit of knowledge about Fourier transforms and Fourier analysis or Fourier series, a little bit of understanding about Fourier transform from your I mean basic mathematics classes or signal processing or signals and systems, you know that if you have a time domain signal, you can go to a frequency domain signal. Okay, this is one of the Fourier transform you have studied. But if you have a real space signal, you can essentially go into a inverse space signal using the same Fourier transform. So there are two types of Fourier transforms. One is time frequency Fourier transform. Another is real space to K space Fourier transform. Okay, this is the exact thing which is basically useful in analyzing crystals, in analyzing even image, I mean, the image reconstruction happening on your mobile phone right now, how the cameras work, how the X-rays work, how the crystals are basically imaged. It's all dependent mathematically on the Fourier transforms, basically. And I don't want to go into the mathematics of it because that's going to take a lot of time. But essentially, what you have, this is E versus K, E versus inverse space presentation. This is E versus real space presentation. E versus real space is going to give you the picture of motion of an electron in real space that you can feel. That if I show you electron is going to go in x direction, you're going to feel it. Yeah, okay, it's going to go in this direction. But if I tell you electron is going to go in uh, kx direction, you're not going to understand what is kx. Okay, that means this, for example, the k vector which you wrote here, it can also be like kx, ky, kz. Okay, but we're not dealing with that. If I tell you, let's say for example, you have an electron going in this direction, you have an electron going in x direction, you can just understand it. But if I tell you you have an electron going in kz direction, or kx direction, or ky direction, or kz direction, you're not going to understand it at all, because this picture is the inverse of this picture. This is obtained by Fourier transforming it, inverse Fourier transforming the real space representation. That's why the band structure is basically the inverse Fourier transform of real space. Okay, so the band structure is inverse space of the band diagram. The band diagram is E versus X. Now what you understand? In order to understand the band diagram, you essentially look at only bottom edge of the conduction band and top edge of the valence band. So it's as if you are zooming into this part, because it's like the minima of the conduction band and maxima, or I should say maxima of the valence band and minima of the conduction band. Okay, once you take, for example, this, you only consider the minimum of conduction band and maximum of the valence band. Why it is the case? I mean, it's also mathematically. I mean, you can understand it from mathematics, but we will go on to that particular detail later on. You consider these two parts, then you essentially have, for example, this E versus X diagram, which basically comes that if you have crystal, you're gonna have energy levels. Let's say, for example, this will be the conduction band, this will be the valence band of it. But actually, when you are considering these flat bands, flat lines, at each of the lines, again, I'm mentioning it, just understand it, what happens. At each of these particular flat lines, this is now E, this is X. So if I tell you that electron in a conduction band is moving here, it is actually, I mean that it is moving in real space. Okay, but but what happens to the same electron in E versus K picture? That is the important point. And that point, if you understood, that's gonna be, I mean, confusing to you people, but you have to think about it a lot, because it's all Fourier transforms, nothing else. But I'm just trying to give you a picture. So if you zoom into this particular picture now, you have a conduction band, you have a valence band, and you know this is E, this is X. At each of the points, at each of these points, like each of the point on the energy curve, each of the point, there is going to be essentially these parabolas. What are these parabolas? Again, you're getting confused. These parabolas are nothing but these EK parabolas. I told you to zoom into the bottom of it. When you zoom onto the bottom of this particular curve, you can basically have this parabolic representation of this particular energy. I mean, if you have this particular black curve, you have this curve. For the bottom of the conduction band, you can approximate it with a parabola, just like this. So once you zoom into the bottom region, you have a parabola instead of this figure, you have a parabolic figure. So each of this parabola exactly lies at this particular point. This particular point. That means this minima exactly lies at this particular point. Electron is present at the particular minima of this particular point. Okay, unless you don't supply it with the external energy. We're gonna see what happens when we supply the energy. Similarly, your valence band is gonna be something like this. This is gonna have, it's gonna have holes. Okay. Now what happens? What happens when you apply the electric field? Now you apply positive, you apply negative, and the electrons are gonna feel force. You know that electric field is from positive to negative direction. This is the direction of electric field. So this is the electric field direction. What happens when you apply positive electrode to a crystal? When you apply positive electrode to a crystal, the electron's potential energy reduces. Why? Let's say, for example, you have a positive charge, you have an electron. The electron, it doesn't need much energy to stay in the vicinity of positive charge. It likes to stay with the vicinity of positive charge just because of the mutual force of attraction. Okay. But on the other hand, if this is a negative charge, then the electron, it will not prefer to stay within the vicinity of negative charge. It's going to feel repulsion, right? Just from your basic 10 plus, like basic class physics. Because of which, when you have a positive electrode attached to the crystal, on that particular side, your electron's potential energy reduces. That means electron doesn't have to spend much energy to remain at that particular point. It reduces its potential energy. On the other hand, when you connect the negative electrode, electron's potential energy increases on that side. Okay, because now in order to stay at that particular place, electron has to increase its potential energy. Electron's potential energy essentially increases when you attach a negative electrode onto the crystal. That is what exactly happens. On the positive side, the electron's potential energy goes down. On the negative side, the electron's potential energy goes up. Remember, these curves were the potential energy curves, potential energy profile. That's what we started with. These are potential energy profiles of an electron. That means on the negative side, the potential energy is gonna go high, and on the positive side, the potential energy is gonna go here. And what is gonna happen when you connect these electrodes? Your bands are gonna band something like this. That means on this side, the potential energy increased because you connected negative. On this side, you connected positive, the potential energy reduced. And an electric field is same. Electric field is in this direction, which is the external electric field. Now what? This was conduction band. This was valence band. Now is the funny part. I should say the interesting part. Because the electrons were present here, electrons were present here, electrons were present here. What is going to happen? They're going to go down the hill. This is just like a hill now. Just like a hill, you have some wheels over here. Earlier, this hill, there was no hill, but now because you applied the electric field, you made this like a hill. Now electron is going to go down the hill. When the electron rolls down the hill, it gives rise to essentially current. That is what basically causes the electric current to flow inside a system. Now the one of the interesting part here is how do these electrons go down the hill? Do they go like a wheel, just like a wheel rolling down the hill, or do they go in some other sense? That is for some other session, and we're gonna discuss in maybe week 3 or week 4. But this is what basically happens when you apply the electric field to these electrons. And in the EK space, what exactly happens? Because you have these parabolas at each of the locations now. You have a parabola here, you have a parabola here, you have a parabola here. Your electron's potential energy at this place is huge, then it's gonna reduce, then it's gonna reduce. So it looks something like this as you go down the hill. So this is exactly how it represents an EK picture. Because you're in EK picture, this is potential energy. Your y-axis is potential energy. So if your potential energy is higher, it's gonna be at higher point. If your potential energy is lower, it's gonna be at lower point. So as you go down the hill, the electron in the band looks something like this. And opposite goes for the holes. You can draw exactly similarly for the holes. Okay, so this is the picture of coming from quantum mechanics. When you come from atom, you solve the Schrodinger equation, you get the bands, and from the bands you obtain these I should say confusing band-like picture, but you then bring it to a reduced Brouillard zone representation, and from it you understand the flow and dynamics of the electron, how the electron flows, and you got the concept of holes. Then from this you move into the real space, which is a little bit tricky. That's why I'm not going in detail of it. It's mostly dealt in higher courses. If you want to understand it from Fourier transform perspective, you should essentially take a course called as nanoelectronics. But here, this because it's an introductory course, we don't want to deal with it. But it's tricky to understand from beginning. From this point, I can understand, but this is exactly how electron moves in a real space, and what exactly happens now when the electron goes down the hill. That's a different thing altogether. That we leave it for next time. But this is the part which I wanted to cover, at least in order to bring us to a common point of the motion of electron and how to go from quantum mechanical picture to get the band band structure, and then the band diagram, and then you can essentially get current flow inside the system or a crystal, because we are all electronics engineers, so we care about how the current flows in this structure. If you don't care about quantum mechanics, but you have to care about the band structure and the band diagram. You can, if you're an electronics engineer, maybe if you're not interested in quantum mechanics, or if you feel it's heavy, you can maybe ignore it. But you have to essentially understand the band structure and band diagram. Okay, so that brings us to the concept, the questions which we're gonna go on, and which we're gonna solve quickly. Now they are like some easy questions, obviously, and let's go to the question first. If you have, let's first maybe, for example, ask if you guys have any questions from the things I discussed, or if you have, or if it has confused you people, or if you have understood something maybe new from it, or if you guys have any questions, you can just tell me in 3 minutes. Then we can solve questions. Do you guys have any question? Yes or no? Maybe if you are listening.
Hello, sir. Good.
Yes.
Hello, sir.
Yes. Yeah, Sanjeev.
Sir, I want to understand what how the current flows uh, uh,
How the
and how current flows uh, uh, where where you have sir consider Fourier transform.
Yeah, that's ignore Fourier transform for now, because it's a higher concept, and they don't deal with these transforms in the introductory courses. But I just wanted to mention it. If you are interested in understanding it from detail, then you can understand it all from mathematics, not from the physical intuition, because it's it's more like mathematical than physical. Okay, that's why I mentioned Fourier transform, but you don't need to go into the Fourier transform description. And how the current flows, that's what I basically discussed. That right now we are at a stage where you have electrons in the band diagram as well as band structure. Then you apply the electric field, you apply certain field, your electron is going to face uh, uh, force because of it. The negative terminal is going to increase the potential energy of the electron, the positive terminal is going to bring it down. So you have this hill-like band diagram now, on which the electrons are going to roll, and they are essentially going to give rise to current flow. Because electron going in this direction, your current is going to flow in the opposite direction. So you have current flowing from positive to negative. That's how you show it in a circuit. Now you have a battery like this, and you have a current flowing in the circuit like this, because your electrons are going this way because of this particular band diagram profile of the electrons. And if your electrons are going down the hill, essentially your holes are going up the hill. Okay, your holes are gonna move up the hill. That's why if your holes move in this direction, the current overall is gonna flow in this direction. Okay, because the current is gonna flow in the same direction as that of holes. That is exactly what it means in the opposite direction of electrons. And this is still week first. We're gonna understand it deeply in week second and week third of this course, we're going to deal with these band diagrams and band structures. I don't think all of these was discussed in week first, but because this is everything is connected to the starting point of how you go from a crystal to a band structure to band diagram and to flow of the current. That's why I felt it's essential to discuss everything in a in a combined fashion. Okay.
Sir, would you please guide some reference regarding uh, Fourier transform on this chapter?
You can just search online. You will get a lot of material on it. Just maybe search online that how you can understand band diagram in terms of Fourier transforms, and you should be able to
Application, sir.
Sorry?
So application Fourier transform of application of Fourier transform.
Application, it's everywhere. Like I'm talking to you, or you're looking at this video.
Sir, only for band diagram.
Oh, for the band diagram, maybe you can, if you want to go to details, maybe there's a PDF or something present from MIT OCW lectures. You should be able to find something. You just search for solid state physics course, and uh, yeah, just search for something like band structure solid state physics MIT OCW. If this doesn't work, then you can go to Charles Kittle solid state physics solid state physics. It doesn't describe it in terms of Fourier transform, but you will get a good feeling from the mathematics of it. But there are very few books which essentially describe it in terms of Fourier transform. Not every book is gonna deal with it because it's a very higher concept. You deal it with these concepts in some of the postgraduate courses, not all, but some of the postgraduate courses, and they are not mostly. I don't know. They are not present in the books. You can just search for it, or maybe you can just search it on any of the GPT engines or maybe LLMs. They can give you good references about it. If you want to understand, you have to understand it by yourself. Obviously, GPT is going to give you just references and it's going to give you a description, but you have to understand each and everything by yourself. How to go from real space and to case space representation. That is the essential thing because
Thank you, sir. Okay, sir, I will check and follow, sir.
and
Then I will
one more
reply
thing,
back.
one more thing. I have a surprise. If you guys are interested, then I can also in one of the sessions. I'm not gonna promise, but if you guys are interested, and if I receive some maybe good number of interest from you, then I have a tool which is basically a solid state physics tool, and I'm not gonna name it because it's proprietary, it's confidential, and but I'll in one of the sessions I'm gonna show you how exactly electron moves. It's a simulation tool, but what it shows you, there are two sections in that simulation. It's divided in two sections. In one of the section, it shows the energy versus x real space energy versus real space motion of an electron. In one of the in on the other side, it shows energy versus k representation. And then there is a there are like controlling knobs. If you control the electric field, you control the magnetic field, something like that, and you can essentially see what happens to an electron in k space as well as real space when it basically when you basically apply the electric field. So in k space you have for example one of the ways, for example, you have a k space, and you know this now you've asked. Let me just spoil it because I showed you this k space E versus k, which is basically like this parabola. Okay, E versus K. You know, it's a 1D. It's here I have shown it a 1D curve, but it's not exactly 1D. It's a it's basically a curvature. It's something like this, and it's like a three-dimensional representation. You got it? So it's like a three-dimensional uh, figure. What are the other dimensions? That's what exactly I told you. There are kx, ky, kz in it. K is also distributed into kx, ky, and kz. And if you look at top of this particular E versus K figure, you look from the above, you're gonna see something like these contours. These are called equi-energy contours. If you look at from the top, because you're looking at a three-dimensional surface, you're gonna look it from the top. You're gonna feel it like two-dimensional. Okay, so these are called equi-energy or equi-energy contours. That is what exactly that particular tool shows you. It shows you equi-energy contours, just like this. And if you apply the electric field, for example, if your electron is here, you apply the electric field and your electron goes here, it's going to show you what happens to electron in real space. It's going to like oscillate in a sine wave, or it's going to be something like this. So you're going to feel the actual motion of the electron in real space. But that's what I leave it to you guys. If you are interested, I can show it in one of the sessions. And because that's really important, I mean, people lack understanding about the k-space and real space motion of the electron. But if you are interested, I can show it one of the sessions. Yeah, that's it. Okay, I think we
Thank
should
you,
go
sir.
on. Okay, we should go on and solving the problems. And let's go on to the first problem. These are like toy problems, which you can just easily solve. And now the 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 I should say purpose of this session is not only to solve problems. You can just solve these problems easily, or you can put it into ChatGPT or whatever you like. It's gonna give you answer in maybe 10 seconds or less, or maybe 1 second. You're gonna solve this all these 10 problems in a minute on a ChatGPT. But that's not the real motive of this. The real motive is to understand it deeply, so that you can apply it to your I should say higher other concepts. Because ChatGPT is not gonna develop your concept. It's gonna help you. I'm not saying it's bad. I'm saying it's gonna help you to understand the concepts in a simplistic way, but it's not gonna do it in a correct way always, or it's not gonna give you the visualization or basic understanding of the dynamics of the any of the concepts. It doesn't apply to electrons, it applies to any of the concepts. So that's it. So for question first, you are okay. Let me just remove this. I think this is, we can remove this. Sure, it's gone. So in the first problem, you have it's saying to consider two materials. You have material A, you have material B. This is silicon wafer. This is borosilicate glass. Silicate glass. And borosilicate glass is essentially silicon dioxide. If you oxidize silicon, you get silicon dioxide. This is silicon, which is mostly used in semiconductors. You guys know about it a lot. Heavily used in semiconductors. And it's about light interaction with these crystals now. Now what happens? We draw this band diagram, and we show that there is a gap between EC and EV. That is exactly what is called as energy gap. What you call as band gap. And this band gap is also visible in the E versus K. This is the band gap. Band gap in E versus K is basically the difference between the minimum of conduction band and maximum of valence band. That is the band gap. This over here is not band gap. This is not band gap. This is the band gap. Okay. It's always you should understand how to essentially locate the band gap. So for silicon, you know that this particular band gap, the value is 1.2 1.2 electron volts, 1.2 electron volts. And for silicon dioxide, it's basically an insulator. That means it has a huge band gap. If you are having a system where the band gap is huge, this is of the order of 9 electron volts. That means the difference between conduction band and valence band. Okay. And that is why also this particular silicon dioxide cannot conduct electricity, because it has electrons in the valence band. A lot of electrons in the valence band. Just like silicon, it has a lot of electrons in the valence band. But these electrons, there are no electrons in the conduction band in case of insulator. And if there is no electron in the conduction band, it's not going to take part in conduction. There is not going to be electric current flowing through it, at least ideally. But here you have certain electrons also, because the band gap is less, because you doped it with certain impurities. You can easily make these electrons go to the higher energy level. You're going to free these electrons and you're going to put them into the conduction band. These electrons are going to take part in conduction. Okay, that's why this is like semiconducting. Semi means like half, partially, and this is insulator. And now you might have guessed what happens in case of metals. There is no gap in case of metals, because metals are like they conduct, I should say, efficiently compared to semiconductors, because one, they have a lot of electrons, and second, they have no energy, no gap. At least if you draw the band structure of a metal, you don't see these energy gaps between the minima of the minima of the conduction band and maxima of the valence band. So in case of metals, like for example, you would see something like this, something like this. There's a crossover between the conduction band and the valence band. Okay, so essentially you don't need any energy to supply to make the electrons free. That's why the metals have a lot of free electrons, and they can conduct a good amount of electricity. And now what happens? It's about the light interaction with the matter, and it's saying that we have to select which of the statement is correct. Band gap of A is 9 electron volt, and all the visible light passes through it. First of all, visible light is a form of energy, so it is visible light is between 400 to 700 nanometers. If you convert it into wavelength, you're gonna get around maybe 2 to 1 electron volts, approx maybe 2.4 electron volts to something like 1 electron volt, because wavelength is inversely proportional to energy. And like these are like the photons that are essentially gonna interact with the energy of the electrons. So it's essentially photons energy gonna interact with the electrons energy. And somehow, like for example, if you have a photon coming in which is in the visible region, 2.4 electron volt. Okay, you have a photon coming in here. It hits the electron. The energy of the photon is 2.4 eV. It's not gonna knock this electron out, or it's not gonna bring this electron here, because this gap is 9 electron volt and you're supplying 2.4 electron volt. So it's not gonna match. What is gonna happen? This photon is gonna get rejected. It's gonna go through. It's not gonna get absorbed in this particular system. If it's not absorbed, it's gonna go through. Nothing is gonna happen. Okay. That means it doesn't interact with it. On the other hand, if you have a same 2.4 electron volt photon coming in, because the gap is only 1.2 electron volt, it's going to hit the electron, it's going to knock the electron up, because it covers the band gap is 1.2 electron volt, but you are supplying with 2.4 electron volt. So additional 1.2 electron volt is going to be with the electron, and it's going to rise up. It's not going to stay here at the bottom of the conduction band. If it would have stayed at this place, if you would have supplied exactly 1.2 electron volt, but you're not supplying 1.2, you're supplying 2.4. So additional 1.2 is gonna give it this additional energy, which is basically the kinetic energy of electron. So additional energy above this particular potential energy band diagram is the kinetic energy of electron. Okay, now that means your photon is essentially absorbed by the electrons. So you have the absorption of photon, visible light, by the electrons. That is why your glass, which is basically the glass used in the window pans and all other transparent systems, they use this particular silicon dioxide system because it doesn't absorb the photons. It lets the photons to pass through. But if you have a silicon, it will absorb visible light. That's why silicon appears non-transparent. It appears like a it doesn't appear transparent to the naked eye. So the essential answer is band gap of A is 9 electron volt and all the visible light passes through it. So this is the answer. And band gap of B is 1.12 electron volt and all the light gets absorbed. Okay. So this is the concept. Now, you know what happens in case of E versus if you have this is a conduction band, this is the valence band, and this is the gamma point. You remember that gamma point I showed in the crystal, high symmetry point, gamma point. This is called as gamma point. You can, and if you go in this direction, it's called as X point. This is called as M point. This is called as R. So what happens if you have a incoming photon? It hits the electron. Electron can go above the conduction band. This is exactly how it happens. But on the other hand, this is the case of direct band gap semiconductor. Direct band gap semiconductor. Direct band gap means these 2 points align at same K value. Okay, but if you are indirect, something like this, like the maximum of valence band and minimum of conduction band are not at same K point, they are at different K point, then if your photon comes in, it's gonna hit the electron, it's gonna bring the electron here, but there's no energy level there. The question is, when the photon hits the electron, why doesn't the electron go in this direction? Why will it go here and not here? Anyone? And this is E versus K. In the band structure, if a photon gets absorbed, we always show that the electron goes up the energy. But why don't we show electron goes like this way? Why can't it go? Anyone wants to guess? Okay, let's discuss it next time. We can just keep this. Maybe you can just come up with the solution, a logical one without without using any LLM or something. It's logical if you think in terms of the momentums of the electrons and the photons, but we're going to discuss it next time. Okay, so let's move on to question second. What typically happens to the band gap of a semiconductor when its lattice constant increases due to alloying or straining? Just give me a moment. So the band gap of a semiconductor, which I showed you like this. This is the band gap of a semiconductor in E versus K picture. If you draw E versus X picture, this is the band gap of a semiconductor. What happens if you put pressure on the crystal lattice? Let's say you have a crystal sites. If you somehow press this crystal, a very very strong press, these atoms are going to come closer, right? When these atoms come closer, now these atoms are like this. Let's say, let me try it roughly, but these atoms become like this now. So you have compressed the crystal. What exactly happens? Because you know that there are electron clouds around each of these atoms. The more you compress these atoms, the more repulsion these electron clouds are going to feel. More repulsion between these electron clouds mean electron's potential energy is going to go up. Electron now has to, essentially electron's potential energy has to increase in order to stay at that particular site around that atom, because there is huge electrostatic potential, electrostatic repulsion, because you're bringing these electron clouds together now. On the other hand, if you just stretch the crystal and if you make these atoms like far away, now they can relax. The potential energy can lower instead of going up. That is exactly the effect it has on the band diagram and the band structure. When you compress it, you essentially increase the potential energy of the electron. If you stretch it, you essentially reduce the potential energy of electron. That means when you increase the potential energy of electrons, what happens? Essentially, you're gonna have something like this. If your band looks something like this, it's gonna look something like this. Oops. This is tricky here because you need to make it like, oh god. So your lattice constant, because of straining, strain means it can be a positive strain or it can be a negative strain, but it's always inversely related. That means your band gap is inversely related to lattice constant. That means as your lattice constant increases, your band gap reduces. If your lattice constant decreases, your band gap increases, because of this logic that I showed, that I discussed here. That means your lattice constant increases means you have stretched the crystal. That means the spacing increases. Spacing increases, the potential energy goes down. That means your band gap reduces. And in case of the lattice constant reducing, that means you have compressed the crystal. That means spacing reduces. That means potential energy goes up. It's as simple as that. It's the simplest notion. That's it. And this is exactly what is basically used in something called as, it's a very active field. It's called as band gap engineering. You know, all of your mobile phones that you are using, the computers from Intel, the processors you are using from Intel, they all use this particular technology called as band gap engineering because of this strain in their transistors. Now, what is a transistor or how does that happen? That's a different story. But if this wasn't the case, then it wasn't possible to get the particular speed of a transistor which it's working right now. So this particular field is always active. How you can essentially tune the band gap of these semiconductors. Okay, so now another question: wavelength of emitted radiation of an electron transitioning from energy level -15 to other energy level of -5 electron volt is, yeah, I'm not going to solve this. This is an easy question. You know that there is energy level of -15 electron volt, and there's an energy level of -5 electron volt. And it is mines because it's potential energy and it's representing a bound system. Okay, that's why it's mines. How do you represent it? For example, if you have an electron, let's say, let me show you like this. If you have a potential, rectangular potential well like this, and if you have different energy levels, you know, you consider this to be as like 0 electron volt. As you go down, your electron's potential energy is going to increase. Okay, sorry, in other words, let me show you like this. What does this minus 15 represent? Minus 15 represents the innermost energy level. Okay, and similarly minus 5 electron volt will represent uh, the above energy levels of an electron. And it's negative, just like I told you, it represents the bound system, that electron is bound to a certain system because of which the potential energy is essentially negative. And now it's transitioning from minus 15 to minus 5, and you need to compute the wavelength. You can essentially compute it using E2 minus E1, which is hc over lambda. So what sort of wavelength will be emitted? Will be the difference between the two energy levels, and the wavelength will essentially be E2 minus E1 divided by hc. Yeah, you solve this, you're gonna get the resulting answer. From my understanding, because this is minus 15 to minus 5, it's gonna be huge energy transition of order of 10 electron volt, and 10 electron volt corresponds to, I don't know, it's 3.8 electron volt is around 325 nanometers. So you go down, it should be somewhere between, it should be 100 or 124 should be the answer of this question. Yeah, you just solve this. Okay, and that means it goes into the X-ray region. It's going to emit X-rays because the energy difference is huge. And what else? What else? What else? Consider particle in 1D box. This is the 1D box I was talking about, where you consider the different energy levels of an electron, and this is the width of the box, and this is the energy E1, and total energy levels are En, n energy levels, like say up to n. What is the ratio of energy emitted when particle makes a transition from N3 to N1? So the particle is making transition from N3 to N1, and again it's going to make it's making another transition from N5 to N1. So there are two transitions happening. You need to find the ratio of energy emitted. It's easy. So the ratio of energy from N3 to N3 to N1 divided by ratio of energy from N5 to N1, it's going to be, obviously the energy it emits, it's proportional to the difference in what should I say, difference in N2, I should say N3 minus N1, the difference in the, oh god, what happened to this pen? It is proportional to N3 square minus N1 square. So essentially you're going to get 9 minus 1 divided by 25 minus 1, so it'll be 8 over 24, so it's going to be 1 over 3. So your energy emitted from N5 to N1 is going to be 3 times more than energy emitted from N3 to N1, which is obvious. So this is going to be the answer of this question. It's from basic physics you have studied in 10+2. Yeah, this question. So you have this is the band structure I was talking about. And you see that there are different points. This is the gamma point. This is again the gamma point. That means it is this point and this point is same. This point and this point is exactly same. If you just fold this particular plot in a circular way, that is exactly how the energy curves look like. You know what you do? This is a square plot. If you just fold this plot, you know that there are these lines. You fold this plot once, and you fold this plot again. It's gonna form a something, a plot like this. It's gonna, on paper it's gonna look something like this. And Once you do that, this gamma point and this gamma point is going to combine. And then you look at this three-dimensional figure, and that is how exactly these energy structures look in a crystal. That is how exactly you look. You look at this particular profile figure. But because you cannot draw a three-dimensional figure on a two-dimensional surface, you put it in like in a this two-dimensional representation, and that's why you depict these particular high symmetry points, M point, K point, which are different directions in the crystal. Okay. Now, what is happening here? It is saying that it's a MoSe2, it's a semiconductor, the molybdenum diselenide, and this is basically the valence band, and this is essentially this should be the conduction band. But let's see what the question says. Which of the following statements is true regarding its band gap if A is a transition? It is mentioning that A is a transition. That means a transition of electron is happening from here to here. Okay. Then if A is a transition, then MoSe2 is indirect band gap. It's incorrect, because if this transition is happening, it's going exactly at same K value. Not this K, but this K, wave vector value. This K is just this K is index. It's indices, Miller indices. But this K is the wave vector. I'm talking about wave vector. Don't get confused. That means this point is at the same wave vector as this point. Once they are at the same wave vector, it's a direct bandgap semiconductor. So it's a direct bandgap semiconductor at K point. MoSe2 has a zero band gap. This is wrong because you see there are gaps everywhere. This is a gap. This is a gap. This is a gap. This is a gap. If there was a scenario that one of these bands come down and it merges like this, then it would have been a zero band gap. But there are always these gaps in the plot. So there is a energy gap in this particular structure. So it's a semiconductor. It's not a metal. Okay. If you look at EK of a metal, they are almost all the time something like EK of a metal. Something looks like this. They are almost merged. Those bands are merged. There is no gap for a metal. MoSe2 is a metal with overlapping conduction valence band. This is absolutely false. They don't have overlapping conduction valence band. And another question, I guess this here. What does the transition X most likely represent? It's saying that what this transition X represents. I guess we overshoot at the time. I'm going to finish it soon, just in 10 minutes. This X transition is essentially representing electron is going from gamma point to some other point, which is here. That means if the wave vector here is k1, wave vector here is k2, electron's wave vector is basically changing from k1 to k2. And it's not possible. That is the question I asked you. That how is it possible? If you have a band structure like this, you have a electron here, a light photon is coming in, the photon is coming in with some energy. It brings the electron here. It doesn't directly send the electron in this direction. Why? Because remember, this is E, this is K, and this K is basically wave vector of electron, but it's also momentum of an electron. Momentum is h bar K. And a photon also has a momentum, although it's massless, but it also has a momentum, h bar Q. Q is the wave vector of a photon. It's associated with the wavelength of the photon. Just like K in case of electron is 2 pi by lambda electron. In case of photon, Q is basically 2 pi by wavelength of photon. You can understand something like this. Okay. But h bar Q is basically the momentum of a photon. This is the momentum of a photon. And because of momentum conservation, a photon's momentum is very small compared to that of electron's momentum, because electron is a particle, it has a mass also. Electron has mass also. Electron's momentum is huge compared to that of photon. You can always compare the ratio of momentum of electron to momentum of photon, and you see that that ratio is huge for electron. I mean, the momentum of a photon is momentum of an electron is huge. What does that mean? That means a photon's momentum is not enough to cause a change in the momentum of a photon, to cause the direction change of a electron. That means if when a photon comes in, this is a photon, it's coming in, it's hitting this electron, it cannot send the electron in this direction because it doesn't have enough momentum to exchange. It's just like Newton's cradle experiment. You have those hanging balls, and if you hit this ball is gonna hit the other ball, it's gonna hit the other ball. Okay, but if you have a smaller ball here and if you have a bigger ball here, if you hit this smaller ball with the bigger ball, it's not going to create any change in the momentum. Although energy transfer is always there. So that means energy is transferred, but momentum is not transferred. Okay, my mom is calling, indicating it's late. Momentum not transferred. So when the momentum of photon is not transferred, electron's momentum is not going to change. It's going to go up in energy, but it's not going to change its momentum. That's why it goes higher in energy. But where does it go? There is no energy level at this place. Actually, there is. I mean, it stays momentarily at this particular position. It can be a donor energy level, impurity energy level, or something else. Let's assume something else. Let's not go into that detail first. But electron goes there. But something happens here. When the electron goes here, there is also something else in a crystal. It's called as phonon. Phonon. Phonon is basically the lattice vibration. Lattice vibrations, when you understand quantum mechanically, you call it phonon. Just like a photon is a vibration of electromagnetic energy. The phonon is basically a vibration of acoustic wave instead of an electromagnetic wave. The acoustic wave is present inside the crystal. That means these phonons are basically, because of the vibrations, these atoms are always vibrating. So a phonon comes in. A phonon is also like a particle, not a true particle, but it comes in. The phonon has enough momentum and it hits the electron and it brings the electron to this energy level. So electron goes in this direction and electron reaches here. It's a three-way process. A photon comes in, hits the electron goes up in energy without any change in momentum. Then a phonon comes in with certain energy. Usually it's very low. The energy for phonon is very low, but the momentum for phonon is high. I mean, it has significant momentum because these are atoms moving. These are atoms vibrating. So it has high momentum. So a phonon comes in, hits the electron, and the electron goes here and reaches this particular energy state. So that is what basically is called as phonon assisted absorption. Okay. So an indirect transition, so that means this particular X here represents an indirect transition. Why indirect? Because it goes from K1 to K2, changing the momentum. But it involves a phonon participation. That is the only way it's possible. Otherwise, electron cannot change its momentum by its own. That means if you take phonon out from a system, how do you take phonons out from a system? How do you take phonons out? Phonon is vibrations. Phonon is vibrations. Vibrations occur because of heat. If you take heat out of the system, out of crystal, how do you take heat out of crystal? You reduce the temperature. That means if you reduce the temperature, let's say 0 Kelvin, this transition is not going to happen. Electron is not going to go to this energy level. It's not going to happen. And it has a lot of implications in space technology, in solar cells, LEDs, blah, blah, blah. So I won't go into details. But this is the exact concept. Okay, so moving on. Consider intrinsic semiconductor, which of the statements is true regarding electrical conductivity. We need to see which of the statements is correct. So intrinsic semiconductor is basically undoped. So if it's undoped, it has a very low electron concentration of the order of 10 to the power 10 per centimeter cube, something called as intrinsic carrier concentration. Okay, that means number of electrons is equivalent to number of holes is equivalent to intrinsic carrier concentration. That is exactly 10 to the power 10 per centimeter cube at room temperature, 300 kelvins. Okay, if you bring down the temperature, what happens is basically if you reduce the temperature, the intrinsic carrier concentration goes down, because intrinsic carrier concentration is proportional to temperature as e to the power minus Eg over 2 kT, where this Eg is the band gap, K is the Boltzmann constant, T is the temperature. So you go on reducing the temperature, that the intrinsic concentration reduces. Once your intrinsic concentration reduces, your number of electrons reduces, holes reduce, you're not going to get electrical conductivity. Okay, so that means silicon conducts at 300 Kelvin, but not at 0 Kelvin. At 0 Kelvin, it behaves almost like an insulator. Okay, that's what Ni as a function of temperature behaves. So it behaves like this. If you go on to reducing the temperature, the Ni is gonna reduce. It's gonna go something like this. It exactly has a different variation, but at lower temperature, Ni is so less that you don't see any conductivity happening in silicon. That means if this is conduction band, this is valence band. All the electrons are in the valence band. Nothing is happening here. Nothing is here. So there is really no conduction happening at 0 Kelvin. The last question, oh, there are two more. I think I'm going to discuss the other two in the next class. We're going to end it here. Or we're going to discuss these three in the next session, in the beginning of the next session. Otherwise, it's going to be extended. Okay, so we will discuss these three basic questions in the next starting of the next lecture, and then we're going to move on to other session. And this session got extended because I wanted to create a framework. That's why it got extended now, because I have created this framework of going from a band diagram to a current flow in a semiconductor. The next lectures will be definitely 1.5 hours always, and I'll try to just manage it, because otherwise it's very difficult to manage the time in this session. If you guys have any questions, you can tell me. You can stay if you have any comments. Otherwise, we are done with today's session, and you can just always look onto this video on the YouTube. Thank you. Oh, God.
Thank you, sir.
Thank you. If you guys have any comments, you can just tell me, or if you want some change in the session, or if you want me to discuss anything else, you can just tell me. Else we are done.